Y'all can start this. I didn't get a decent video from last Thursday. But I think I can work with the video going forward. Anybody completely lost on calculations? Anybody having trouble with calculations? So we did move on Thursday to actual chemistry, atoms and molecules. I want us to continue with that. So I told you last time, let me get to this diagram, that there's basically 4 different types of compounds that are made out of atoms. And the ones we will talk about are covalent compounds, ionic compounds. There's also metallic, and there's this says coordinate covalent. Don't worry about this one. And metallic actually comes up pretty rarely. But I like to make this chart, and I'll remind you of it because covalent means all the atoms involved are nonmetals. So there's atoms and there's nonmetals, and there's in between that we call metalloids. Okay, so metallic is, so there's all nonmetals for covalent. These are molecules. These are what we refer to as molecules. Metallic is all so covalent, they're all nonmetals. Metallic, they're all metal. And when you have metal and nonmetal, that's ionic. So really this chapter is focusing on these 2 things. So over here in this corner, these are the nonmetals. Ignore the noble gases for this. But in here, these are the nonmetals. These are what make molecules. And hydrogen's also included in that. The color coding over here isn't telling you that. But I guess what you would want to look at, oh, if you've got this handy, you might have that out for today. So backing up one section. So, and this is just essentially a typo. This really shouldn't be included here, the noble gases. But everything green over here, including hydrogen, those are the nonmetals, those make molecules. Everything else is a metal except for the metalloids. Metals and nonmetals. So I kind of ignore these. It's just that they sometimes behave as a metal, sometimes as a nonmetal. But okay, so if it's made up of a pure something from here or some kind of alloy from all these, we would call it metallic. It's ionic if it's got metal and nonmetal, and if it's made up of only nonmetals, it's molecular. So we land here. So the next section starts on molecules and molecular compounds. And then the next section after this one that I'll go over talks about ionic compounds. But I want to pause here and mention when we do what we call chemical formulas, that little chart there that shows these, we focus mostly on stuff like this, but there's one more that I would have put in this chart that says the empirical formula. And so of course these just, so you've got your empirical formula, and then moving to the right you get more and more information about the molecule. But let me show you. Also, I would call this perspective drawing. Oh, structural formula. I would call that, if it were me, I would say structural diagram. It's not really a formula in my head anyway. But I'm not going to ask you those. I'm not going to say, is this a structural formula? Is this a molecular formula? Whatever on a test. But let me give you a little more info. Let's say, let me draw a simple diagram of a molecule. But I want it to be a little bigger than that one. So if I gave you this molecule, notice these are all nonmetals, hydrogen and carbon. Is that going to work? I did get here last week. Can't remember quite where we left off, but all right. That is this. It's just a diagram showing you what's connected to what. That's a molecule. Probably should do this. OH is so common that we sometimes write them. Okay. So that's this. Now if you wanted to do the molecular formula, you would just add everything up. 1, 2, 3, 4 carbons. So C4. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. So I'll say H8. And there's 2 oxygens. So I'll say O2. That's the molecular formula. There's one more thing you can do in this empirical formula that I'm talking about. One of the reasons it's confusing, because you look at it and you go, why the hell would you do that? But what you do is, well, I could say you divide by the lowest number there. There's another way of doing this that I think is a slicker mathematical way to do it. But let's say it was just 4 and 8 and there were no oxygens. And I said, I'll go carbon, I'll do hydrogen here, I'll put the 8 here. And I'm going to do this thing that you learned in math years ago in high school or grade school somewhere, where I split them into their prime factors, meaning 4 is 2 times 2, 8 is 2 times 2 times 2. Oh, not the greatest example, but you cancel. So I cancel a 2 with the 2, a 2 with the 2, and what I have left is 1 over 2. That's the empirical formula. But let me bring the oxygen back in there. And I'll show you, it looks weird when you do it this way. How many was that? This was 2, this was 8, this was 4. This will look weird, but it still works, because you never would do this in math. But now I'm going to add the oxygen. I'm going to do the exact same thing I did before. Put the 4 here, the 8 here, doing this right here, 8 here. I'm going to put the 2 here for the oxygen. So that's what I did before. But I'm putting this down here as if this is a totally valid thing to do in math. Put another line and make another denominator. But this still works. 2 times 2. And then just 2. And again, cancel as much as you can. But it has to cancel through all of them. And that's as many as I can do. So I'm left with a 2 here, a 4 here, and a 1 here. So then the answer would be carbon, 2 hydrogen, 4 and oxygen, 1. But here's the weird thing. Well, just one detail at the end. That would be the empirical formula for this. So its empirical formula is C2H4. Oh, but yeah, this weird little detail. In chemistry, there's a lot of odd little circumstances where we don't write the 1. I don't know who came up with that. 200 years ago or whatever, but we just don't write the 1. If it's 1, we don't write it. So that's the empirical formula. And this is the molecular formula. And this is what I'm saying. It's this and this are really better descriptions of this molecule rather than this. This is kind of an antiquated thing. There was a time, I don't know, somewhere mid last century and earlier, where one way of identifying a compound was burning it, doing combustion on it, collecting the products, and doing a calculation. And the truth is, at the end of that calculation, this is all you could get. So let me try. So this is the empirical formula for that. This is the molecular formula. This is the structural formula, structural diagram. And there's more and more I could add to this, but that's just more and more information. This just shows you what's connected to what. It really is a diagram of what's connected to what. If you wanted to know what it looks like three-dimensionally, you'd have to at least start using this dash wedge thing that they're doing here. These are the types of things computers generate. I'm not a graphical artist, so I wouldn't be able to draw those by hand very well. So just picture it this way. Empirical formula, molecular formula, structural formula. Going to the right, you get more and more information. An empirical formula, if it strikes you as a silly thing to do, it kind of is. It's kind of antiquated to think about molecules this way. So this is a good point to bring up. Do it with this one? You can. So there's this molecule, and then how about this molecule? This one's C4H8O2. Yeah, I think I can do this. This is a double bond. We'll talk a little bit more about molecules. H there, H here. Two, three, four, five, six, seven, eight. Good. So what is the molecular formula for this new molecule?
It's the same.
It's the same, and that's the point. Okay, for one thing, these have the same molecular formula, but they necessarily then also have the same empirical formula. So that's one thing to know. Oh, another thing to know is these two things called isomers. Isomers have the same molecular formula, but they're actually different structures. They're different things. This would have different properties than this. So if you were in the lab trying to identify this 70 years ago, you'd do combustion and this is all you could figure out. You wouldn't know whether you have this or whether you have this. You come down to this, and there's a whole class of molecules that are all isomers like these. So those are called isomers. They'll have the same chemical formula. What else was I going to say? I think that's it. So isomers. Again, this just shows what's connected to what. Three-dimensionally, this would even look different than that one. Seems like there was something else I wanted to say, but I guess not. So empirical formulas, molecular formulas, structural formulas, isomers. I have a list that I'll give you of the questions at the end of this chapter. Thinking, should I go there? Structural formulas. Yeah, let's go ahead and do some of those. Let's get down to so I'll do these. Since I'm giving you the periodic table for the test, you'll have to learn either by using that or by using this, where the line is between metals and nonmetals and metalloids. These are two I would say practice with. I think we did this. Didn't we do this? This is like the last thing we did last time. Mn, manganese, it's right here. Is that a metal, a non-metal, or a metalloid? Metal. It's a metal. Those are easy questions. We get to the empirical formula stuff. Structural formula is 45. Okay. I'll do these ball and stick things. It's worth knowing, just because of these diagrams, I won't use them on a test. Let chalk go. Not those, but those are fine. It's these space filling models that I'm not going to put on a test, so I try to avoid them as an assignment, but it's worth knowing. I guess put it up here. That, well, just write this down. When you see one of these with colors, black is always carbon, white is always hydrogen, red is always oxygen, and nitrogen is always blue. Those four are standard colors used for these types of diagrams. But if I ask you empirical formula, molecular formula on these, you see 6, so for the first one, benzene, you see 6 black ones, so that's 6 carbons, and you see 6 white ones, that's 6 hydrogens. So you would say for the molecular formula, straightforward enough, right? And then what would the empirical formula be?
CH.
It would just be written like that, CH. If I did this real quick, C and H, and I still can't draw on the chalkboard. And I said split it into its prime factors, everything cancels. You end up with 1 over 1, but like I said, we don't write the 1, so I've just got CH here for the empirical formula. Don't get confused by that because it's so simple, it's really that simple. Empirical formulas, though, just aren't used very much. And I guess the whole reason they wanted to use this as an example is, here's acetylene. But just like the example I showed you before, that's going to have the same empirical formula. So the numbers in the empirical formulas are just showing you a ratio of atoms to atoms. That's straightforward enough. 247. I'll try not to do the red ones so you have something to practice. This I didn't put in your questions. Like I said, I've got a Word file I can upload that's got all the ones that you should practice. two substances have the same molecular and empirical formula, does this mean they have the same, does this mean they're the same compound? But of course it doesn't, because for one thing, these are not isomers, but they do have the same chemical compound, same empirical formula. But I showed you two examples of some that do have the same formula, molecular and empirical. Those were isomers. So the reason for this is because of isomers. If they have the same molecular formula, same empirical formula, they can still be different compounds because of the way they're connected up, what's connected to what. I think y'all could do these, but I'm going to leave the red ones. Are we down to 52? All right, good. Let's go on to, we'll go on to ionic compounds. We'll spend most of our time talking about ionic compounds. And most of what we'll do for test 1 out of this chapter is about naming these. I mentioned this last time, and you should know this because it's something you can get straight off the periodic table, but so all of these nonmetals will be neutral, meaning they'll still have the same number of protons and electrons when they're in a molecular compound. When the metals are in a metallic compound, they're still neutral, but when it's in the ionic compounds, they're charged, and it's the charge that's pulling them together. There's a positive charge and a negative charge, and they're being pulled together. That's what makes them stick. That's what makes them bond. That's why they're called ionic compounds, because the bond is ionic, as opposed to covalent for molecules. And many of these charges are predictable just by looking at the periodic table. All of these will be +1, all of these will be +2, and there's only one +3 to think about, it's aluminum. So all +1, all +2, and then +3 for aluminum. And then if I skip the metalloids and I go on over here, you can predict all of the charges for the nonmetals as well. So I would look at carbon, not count carbon, but I would count the next 4 to the right and go 1, 2, 3, 4. Carbon, if it's charged, will be a +4, a -4. So this is gaining negative charge, gaining 4 electrons. So carbon and silicon will do that. Nitrogen and phosphorus will be 3. Oxygen, sulfur, selenium, tellurium will be charged 2 if they're charged. These will be all charged 1, and just ignore the. So that's simple enough straight off the periodic table. I'll give you a list. There's predictable charge. Those are the ones I just named. And then there's, let's see, ions in this world. There are atoms. Where the charge is not predictable. And let me point to those. Here are the ones that are not predictable. This whole block here in the middle, those are called the transition metals. So you've got your, I mentioned these names last time, but you've got your alkali metals and your alkaline earth metals, and then when you get to these metals, we call all of these transition metals. These, they're not predictable in the sense that they can have more than one charge. So if I just said, did I get this far last time? Wow. Okay. I like this diagram, but I don't want to go past it. Show you. predicting ion charge. They're still, so there they are, the predictable charges. Compounds. I want to complete my list there. I know they had good examples down here. Oh, they probably do it in the naming. All right, well, let me back up here. So if I said here's no, I want to complete this list. Let me write this. A third one, or all right, we're in a chapter where I said we're talking about ions and ionic compounds, and I told you it's the nonmetals that make molecules. But molecules have a little cameo that show up in the discussion of ionic compounds. There are some types of molecules where if you added up all of the electrons in the molecule and all the protons in the nucleus, it ends up being unbalanced in the number of protons and electrons. We call these polyatomic ions. And that's where things start to feel less than straightforward for ionic compounds. But okay, so I'm back here. I mentioned the ones that are completely predictable. And you can think of an ionic bond or an ionic, I think these diagrams will work, an ionic compound. Think of it like this. You've got a sodium atom that's nice and neutral. It's got 11 protons, 11 electrons. And what happens is it loses one of its electrons. So now it's going to be charged positive. And you think of this is a chlorine. Same idea, except it's going to gain an electron to make it negative. And then this negative thing and this positive thing come together to make the bond. I guess I went over that in my head over the weekend because I feel like I did that already. There's those. So another major difference between molecular compounds and ionic compounds is this is what it looks like on an atomic scale. They just line up like you've got chlorine, sodium, and then going down, you've got sodium, chlorine, and they just alternate, and you get that whole face, and then they alternate going back too. If you go back a row, you've got chlorine, sodium. It's these ionic lattices that they're called. You could also call them crystals or a crystal structure. Ions arranged in a lattice. Molecules don't look like this on a molecular scale, on a tiny scale. But this is what they do. Picture them being either positive or negative and coming together, and then they just build these nice, neat arrays. That's what ionic compounds look like. You have a picture here, like if you just dumped out a bunch of table salt, you looked real close, you'd see some chunks about this big, be a chunk like this, but it'd be a certain size, and then smaller chunks could be even smaller chunks of these, but truthfully your eye can't really see this small. But the idea is ionic compounds are almost always this crystal type structure. Sometimes there's crystals that are really hard like a quartz crystal. Some of them they're very brittle like salt, table salt, that you can just crunch up and make it as fine as you want. So worth mentioning, okay, here's a question. Based on what I've already told you, you can decide which of these are ionic compounds and which of these are not. These. Do you know how to tell? Nitrogen and oxygen, this whole molecule made up of nitrogen and oxygen. Those are nonmetals. There's nitrogen, there's oxygen, so that's a molecular compound. Sodium and oxygen, well here's oxygen, it's the nonmetal. Sodium's over here, it's a metal, so that's an ionic compound. You see? So that first chart I always draw, molecular compounds, that is molecules, are made up of all nonmetals. And then it's metals and nonmetals that make up the ionic compound. Calcium and chlorine, is that ionic? Calcium is over here. So that's an ionic compound. What about SF4? There's S and there's F. So is that an ionic compound? It is not. That's a molecular compound. All right. So those are straightforward enough. Chemistry and life thing. Okay. Finally, we're getting to what I was trying to get to. So there's those three things. So we're still really here dealing with these, the predictable ones.
Wait, does SF4 not have a charge itself, like you said there's the polyatomic ions?
No, there was no charges involved in SF4.
Oh, I see what you're saying. But it's not an ionic
If I
compound.
drew SF4, I would draw it like this with lines. These are the covalent bonds. We don't even draw that for ionic. I mean, you would never see, like the example for NaCl, Na plus and Cl. You'll never see us draw a line between these two things. Really, the only way to draw this compound would be to go NaCl, 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 and try to build that array to see. But we never draw ionic compounds. That's a molecular compound. The ones that have lines, those are the molecular compounds.
But can't sulfur only make 3 bonds? 3 covalent bonds?
Say again?
Can't sulfur only make 3 covalent bonds?
Can sulfur?
I might be talking out my butt, I don't know, but...
Oh, yeah, that's a polyatomic ion.
Okay.
That's probably what you're thinking.
Yeah.
It did say SF4, didn't it?
Yeah.
We'll get to those.
Okay.
Yeah. But it is a molecule. It just happens to be charged. What do I want to do here? Okay, here's the thing. Aluminum, if I said, they're giving you plenty of clues here. Write the empirical formula. So when it comes to ionic compounds, we do the empirical formula because there really isn't a molecular formula. I mean, try to make use of the book since we actually have it. So this is what NaCl really looks like. There's not really a little unit of some Na and some Cl. It's just, it's kind of, in a theoretical sense, it's infinite. They can be huge. They're not really infinite. But this, so an empirical formula is just the ratio of the atoms to each other. And this is 1 to 1. If we added up all the chlorines here and all the sodiums here, they would be the same number. And then the empirical formula is really the only thing we could write. I mean, this would be like, some chunks would be because they're going to balance the positive and negative. And then another chunk sitting right next to this one could be. So we just don't bother with trying to make the accurate molecular formula. We always go with the empirical formula because it's going to be 1 to 1. Anyway, so they gave you the hint, which on a test I would want you to come up with on your own, but it tells you Al3 plus and Cl minus. But if I just did this and said, give me the empirical formula for when you have aluminum and chlorine, you would look at the periodic table and come up with this yourself. This is the other case where we don't write the 1. This is saying it's a +3 charge. We don't put a 1 there when it's just 1, we just put the negative. If it was positive, we would just put positive. So I don't know why chemists do that, but don't get thrown off by it. So what you have to do when you make the empirical formula is you have to make the charges balance. So if I have Al there, and it's got a +3 charge. Let me do this. I'm going to need 3 chlorines that are 1 negative to make it balanced, charge balanced. That's the empirical formula. So it's that charge balancing that you pay attention to come up with the empirical formula. All of these are pretty straightforward. Like this had a 3+ and a 1-. This is one of those polyatomic ions, NO3. You have to get to where you sort of recognize these. But if I wrote that one, I would go, is that Mg? Mg2+, and then NO3. You put it in parentheses and you put a 2 there. So we got a -1 charge and a +2 charge. So to get them to balance, I just scale this up. 2 of those to go with 1 of these. That's the empirical formula for that one. Do you see that? Okay, if anything's throwing you off, it's the polyatomic ion. But that's just a small molecule that happens to have a charge on it. Let me do some that have higher charge on the... What if I had lithium and nitrogen? So lithium is over here, and nitrogen is here. So what do I have for charges? What's the charge on lithium?
+1.
+1, so I'll just do that. Charge on nitrogen?
-3.
-3. So if I want to make these balance, I have to have 3 positive charges to go with the -3. That's the empirical formula. You just make the charges balance. Does that make sense? Does it not make sense? All right, and I saved this one because it's when it's 3 and 2 or 2 and 3, it's the only time, I think just about the only time, you ever have to scale it up to something. It's sort of like the least common multiple. But, so I've got aluminum oxide. What I end up doing is scaling each one up to 6, meaning if I have 2 aluminums, we end up with a +6, and if I have 3 oxygens, I end up at a +6. So you end up, when it's 2 and 3 or 3 and 2, you have to do that least common multiple kind of game. So really, there's no way to get to a +3 with oxygen, and there's no way to get to a -2 for +3. There's no way to get to -3 if I just wanted to use 1 aluminum, and there's no way to get to a -2 the other way. So you end up having to scale them both up a little bit. And I think that's as tricky as they get for charges. Does this make sense? I do have some of those for practice. I think we got to go to naming. It's got to be the end of the chapter. Okay. This chapter says naming inorganic compounds. The difference between inorganic and organic this is just an odd way to bring it up the way they have. But just think of it as the inorganic compounds are mostly ionic compounds. Because that's really what this chapter is doing. It's going through ionic compounds. So the next one in my list that were the unpredictable charges that weren't predictable. So they start here and they show you some of the predictable ones. But here we are with iron and copper, sort of the canonical examples. Iron and copper, there's iron and there's copper. They're in the transition metals. And here's the thing about those, is there's such thing as Fe2 plus. So when I say they're not predictable, if I just say iron or I just say Fe, there's no way for you to know the charge on it. I have to tell you what the charge is because it could be either +2 or it could be +3. And copper has a +1 and a +2. I'll do another example with those. So here's the thing, so let's say so there's my metal, and if I want to use for a non-metal, let's say I use nitrogen again, which would be 3 minus. You would have, do it over here, Fe2 plus with nitrogen, which is 3 negative. What you would get for a formula here is Fe3 in 2. Do you see that? But if I wanted to put nitrogen with this, it's just going to be Fe n. In the name of it here, I'm not sure where they mention this, but when you name these, like this is, this was iron 2. Nitride. This one is. Let me mention this. Kind of skipped over it somewhere in the previous chapter, I think, or maybe it's in this chapter. All of the nonmetals, when you write the name like this, you put IDE at the end of it instead of its typical ending. Like carbon becomes carbide, nitrogen becomes nitride, oxygen becomes oxide. You get fluoride, chloride, sulfide, phosphide, bromide, iodide, selenide, astenide, it's astentide, it's astatine, arsenide. So, and then there's also hydride, and then all the metals just keep their normal name. So that's why I've written nitride here for N. Nitride here for N. So if I sent you to the lab and I said, go get me some, if I just said, go get me some iron nitride, you'd head down the hall and then you'd realize, wait, does he want this or does he want this? So part of the name for these transition metals, the ones that have more than one charge, this has to be included in the name, meaning I should have said iron 3 nitride, and then you'd know you're going to get this. Or I might have said iron 2 nitride, then you would know you were going to get this. So that has to be in the name for these that have variable charges. Important point, I'll just leave that one there. These that have predictable charges, go back to, let's do F negative. So the formula here would be MgF2 to get the charges to balance. And we would call this magnesium fluoride. But there's no need to put a number here. I mean, if you say magnesium fluoride to a chemist, there's only one way you can put that together. There's none of this more than one way to make it. There's only one way to make magnesium fluoride, because magnesium is always going to be +2. And fluorine is always going to be -1. You see that? So it's superfluous to put magnesium 2 fluoride here. So the number, you never put a number with these that are totally predictable. You put the number with the ones that could have more than one charge. So that's why this is iron 2 fluoride. Oh, and the 2 is referring to this charge, not this subscript. Make sense? Okay, there's those two. So in my list, I gave you the ones that are predictable, and then there's the ones that are not predictable from the periodic table. That's like iron and copper here. And then the third type of ion you might have, there's more than one naming system. So you would call this iron 2, and you would call this iron 3, copper 2 and copper 1. This older system, I won't put this on the test, but you see this in labs sometimes. That one's called ferrous. So then this would be, which one is that? 2 there. So this could be called ferrous nitride. But don't worry about that naming system. It's not that systematic. Okay, so here's a couple of polyatomic ions. This one's called ammonium, this one's called hydronium. These can get in compounds too, but let me scroll down some. So this chart, these are, so you don't have to memorize the different charges for copper or iron. I'll always tell you those. But that's just showing you more of these ions. 10. You don't have to memorize those. Hydride, oh, here's where they tell you oxide, hydride. I have a better list of these somewhere where it's not all split up like this. Like what you really want is one chart that's got all these polyatomic ions on it. I'll give you these on a test, just be able to use them for naming. But this book has them scattered everywhere. And the charges aren't really predictable in any way. They just have to be known. But let's say, so this is called cyanide. This is called peroxide. It's got a -2 charge. So we'll go about doing some naming with these. These, like chlorate, these are just in general referred to as oxyanions. ClO4, ClO3. So what I'm about to explain is just a pattern with polyatomic ions, specifically around halogens. So they're using chlorine. Chlorine doesn't do this, but chlorine and bromine and iodine do this. The example they have there, this one. This is called perchlorate. This is called chlorate. This is called chlorite. And this is called hypochlorite. If the Cl were Br, if it were bromine, we would just be replacing the chlor with brome, so we would have, go ahead and draw it. So the pattern here is 4 oxygens, 3 oxygens, 2 oxygens, and I'm not going to put the 1 there. And these all end up being just 1 negative. In terms of this naming, you've got perchlorate, chlorate, chlorite, hypochlorite. There's also such thing as BrO4. These are all negative. So this is bromate, bromite, hypobromite, and perbromate. So you're just changing the chlor to brome. And the same thing works with iodine, but it's iodo. But like I said, I'll give you a list of these to use. You don't have to memorize all these polyatomic ions. I'll give you their name and their charge and their formula. That way you can just focus on naming. So those three pieces, the predictable ones, the not predictable ones, and then the polyatomic ones. Now we've hit all of those. This is what I just explained about using a different halogen. I suppose this is worth mentioning too. So all these oxyanions, so I went through this, but this is nitrate, and when it's 2 oxygen, it's nitrite. But if you look at nitrogen, and you look just below it, we've got a phosphorus. There's such thing as phosphate. I don't think there's such thing as a phosphite. But if you just replace this N with the P below it, then it would be phosphate. Sulfate and sulfite, selenium, so there's selenate. If this was Se instead of S, so S is here, and there's selenium, then it's selenate. But like I said, I'll give you a list of these. So they're somewhat systematic in the way they're named. There are stranger ones. There's phosphate. There's such thing as carbonate, hydrogen carbonate, dihydrogen carbonate. -2. Carbonate, -2, another polyatomic ion. Let me do this. So picture hydrogen being charged positive. Hydrogen's a weird one. It can be H negative and it can be H positive. But picture I've got carbonate here, and I've got a plus charge here that I'm going to connect to this carbonate. Once that plus charge comes in, it eliminates one of those negative charges. So that's the charge on hydrogen carbonate. And dihydrogen carbonate ends up being neutral, because one more positive charge coming in here to cancel that. Now we've got 2 of those, so that's hydrogen carbonate. Dihydrogen carbonate. There is dihydrogen carbonate. There's a similar progression here for phosphate. So there's hydrogen phosphate, there's dihydrogen phosphate, and then we get all 3 of them on there. You could call it trihydrogen phosphate, but that one's an acid. So I want to get to some naming. All right, here. If I tell you SO4 is sulfate, and these polyatomic ions, they're fully predictable. Maybe not from the periodic table, but there's only one charge that goes with the polyatomic ions. So what would you call this one? So that's sulfate. Could you infer the charge on sulfate just looking here? What's the charge on potassium? It's on the far left. So how many positive charges are here? You've got 2 potassiums, so you got 2 plus coming from the positive side, and the SO4 then is 2 negative. So you can infer that charge. So what would you call this? If SO4 is sulfate, The metals, you just use the name of the metal. So this is potassium sulfate. There's no other way to make potassium sulfate other than to be K2SO4. Because there's no subscript there, I don't have parentheses around it. Maybe it helps to have that since there's no subscript here. But there's only one thing you could call this, potassium sulfate. It's not potassium 2 sulfate or anything weird. That's the only way you could make potassium sulfate. If I had, so you can have Fe2 plus and you can have Fe3 plus. Let's say I had this. Let's say I also had 2 plus 3, so this is going to have to be 2. What would you call this?
Iron sulfate.
Iron sulfate.
Iron 2 sulfate?
Did you say the number? I didn't hear you. You said it first. Iron sulfate, you're getting close. But if this is 2 plus, then this has to be, or no, 2 minus, then this has to be 2 plus, which means this. So this is iron 2 sulfate. And this one, if you saw this formula, the only thing you could name this is iron 3 sulfate. If you were looking at this, and I said, let's say this was on the test, and I said, name this compound, and then you look in the notes I gave you to use on the test, and you see that in the notes, SO4 2 negative sulfate. You could do this, you could go, okay, there's 3 of those. For a total of -6 charge here. And these have to balance to 0. And then you could look at the Fe and go, there's Fe, there's Fe, and somehow that has to add up to +6. And then you would go, okay, I got to split that +6 among 2 irons. So 3 plus. And that's how you would figure out it's iron 3.
We don't need to do that for full credit when showing our work, but we can just do.
No, if you can figure it out without sketching anything out and just throw down iron 3 sulfate, you're fine.
Okay.
That's just my quick way to outline the thought process. So yeah, it's not 100% predictable, the charge on these, but if I gave you this to work with, well then you can predict which one of the Fe that it is. So when I say it's not predictable from the periodic chart, but it might be predictable when I give you a formula that I'm telling you that's a correct empirical formula. What would you call that? You would end up having to infer the charge on the iron. Maybe we should look at some of those at the end of the chapter. I almost want to skip these where it says organic compounds, the molecules. Maybe I'll come back to it, but think about test 1 having mostly ionic compounds for naming. Let's go to, what else do I have? So those all have to be named. That's 2. Well, It's at least all the way down to, I know I have a good batch of these naming ones down here. The chlorite and chlorate and all those, I said I would give you. But this says, so I'll just write these, because there is a trick in there. So A, B, chlorate. Like I said, I'll give you these, but chlorite, well, that was this. Was ClO4, negative ClO3, negative ClO2, negative. So perchlorate, chlorate, chloride, hypochlorite. What did they give me here? Chlorite. So that's A, chlorite. Chlorate is this one, which is C. Perchlorate is D, hypochlorite E. So that's E. That was D. But what I'm getting at is, what is B? You see, did I name the right one? Yeah, what is chloride? I'll tell you, because you've just forgotten. It's just this. This is chloride. It's the charged form of chlorine. So that's kind of a trick question, asking that all that together. What should we do? CUS. So, this is the metal, this is the non-metal. Can you find this on the periodic table? What will its charge be?
-2.
So this is, so sulfur is 2 negative. All right, copper is in the transition metals. And those are the ones you can't predict by looking at the periodic table, but you can still predict which copper this is. There's an implied 1 here and an implied 1 here. So if we just have 1 plus 2, I mean -2, and that adds up to -2, and I've only got 1 copper, which adds up to something, and together they equal 0. So what's the charge on this copper?
2.
2 plus. Now, name it. What do you call this?
Copper 2 sulfide.
Yes. This is called got it? Where was that? Where was that? Oh, it was here. All right. Ag2SO4. You've got that in your notes. SO4 is 2 negative and it's called sulfate. So what would you call this? Ag is down here. Ag is silver. So what area on the periodic chart is it?
Transition
transition metal, so the charge is unpredictable. The exceptions here, I think it's these three that are actually predictable. Like zinc is always +1, and silver is always +1, and I think cadmium is 2. So silver, this isn't a great example, because that's one of them that's an exception. There are a few exceptions, but I don't want to do that one. This would just be called silver sulfate. You might think it should be called silver 1 sulfate. I wouldn't count that wrong on a test, because silver is in the transition metals. But like I said, zinc, silver, and I think cadmium are actually, they only ever have one charge. They're the flukes of the periodic table, the flukes of the transition metals. What else should we do here? Oh, this is called acetate, CH3COO, and there's calcium. Calcium's on the left over there, not in the transition metals. So this is acetate. What would you call this? It's just calcium acetate. That's what that's called. And since calcium has a completely predictable charge, you don't have to say calcium number acetate. It's just called calcium acetate. What's the charge on acetate? Oh, what's the charge on calcium? +2. And there's 2 of these things in there. So what's the charge on these?
-1.
-1. Calcium acetate. Did they write that different? CH3COO. So if you have this in your notes, then you could name this. You've got calcium from the periodic table. Or let me do this. There's calcium, and the periodic table tells you that's the charge. You've got a 2 there, so you know you've got CH3COO. You know that all this adds up to 2. And they have to balance. So this has to be -2 to balance, and then you look up here and go, oh, I've got 2 of these. I've got to split that -2 between 2 things. So then you come up with that. Just a thought process. But it's called calcium acetate. It's not called calcium 2 acetate, because the charge on calcium is totally predictable. And same with the polyatomic ions. Charge is totally predictable. What else do I have for this chapter? So it's a handful of naming. And then I might have had yeah, that's what I didn't mention. Let me go way back here. Just so I have it included in the same discussion. backing way up here. I said this will help knowing, at least when you're reading the book, in a lot of cases. I mentioned the empirical formula, the molecular formula. Let me come up with an example. That. All right. That's hydrogen. What's the molecular formula for this? It starts with C5. H would come next.
H8.
H8.
3.
What would be the empirical formula?
The same thing.
Has to be the same thing. If I tried to do this game, got a 3 there, an 8 there, and a 5 there. Now I split them into their prime factors, which you get a 1 and a 5, 2, 2, 2, and a 1 and a 3. Nothing cancels. You see that? If you do this prime factor thing. So that would be the empirical formula too. But what I wanted to show you is there's the empirical formula, there's molecular formula, and somewhere in between the molecular formula and the structural formula, let me make that a little longer, just to emphasize something. So this is that structural formula. Like I said, I would call that a structural diagram. So somewhere in between, so you've got your empirical and then you've got molecular formula. And what is it now? 1, 2, 3, 4, 5, 6, 7. How many H's are there? 12? Is that right?
Yeah. 13.
12. I only see 12. 8, 9, 10, 11, 12. It's 12. And it's 3 oxygens still? All right. 12. Okay. What was I going to say? Oh, somewhere in between this and this, you can do things like this. There's CH3. CH2, CH2, CH2. That's these. CO for that. And then another CH2 for this. And then this last one we go. Okay, I would call this, just to have something consistent for vocabulary, I would call that a diagram, not a formula. And then there's empirical formula, and then there's molecular formula, and this I would call because, and I mean in between here and here in this chart, because you're getting more, still getting more and more information. You're still missing a lot of information looking at it like this. And after telling you about isomers, you realize there could be several molecules that have this exact same formula. But this is getting a little closer to this. It's giving you some of the structural information in it. You see what I'm saying? So I would call that a structural formula. Like I said, I won't ask you these vocabulary words on the test, just if you want a consistent naming. And then I would call, there's one more thing you can do with this. I can go CH3, and these CH2s, I can go CH2, 3, that's those, and then go CO. And that I would call condensed. I would call that the structural formula. I would call this the condensed structural formula, because you can squeeze some things in like that. Another book I've used actually did this, in my opinion, did it correctly. This book is just, I don't know why textbooks don't follow standard. So I would call this a structural diagram. I would call this a condensed structural formula. I would call this a structural formula. And then this molecular formula, getting less and less information. This is what you really want to see what's connected to what. But you can still do this, and you can still do this, and you can still do this. Less and less information coming along for each one. I don't remember why. I wanted to go back and do that. Exercises somewhere in here. Towards the end, probably that. So rather than the chemical name, if you wanted to know if these are isomers, so here's 4 pictures, 4 different molecules. You would need to find its molecular formula and then look at the structures and determine whether or not they're different structures. Maybe, oh yeah. Still in between here and here, there's even this weird hybrid between formula and diagram. CH3 with a covalent bond here. I don't know if I want to give you these questions. Give the name. If you can take that structural diagram and do molecular formula and empirical formula, I think I'm good with that. So I guess that was it for this chapter. What I want to do, take a break, and I'll cover some stuff in chapter 3. And I expect to get part of chapter 3 done between today and Thursday. So the test will be calculations, problems I give you in the back of the book for chapter 2, and then a little bit of chapter 3. But let's take a little bit of a break. I don't know, 10 minutes, 15 minutes. Let's call it 15 minutes. And I'll look over what I'm going to do in chapter 3. Actually, I'm going to post these. So I do have these on in a Word file. The ones to do in the back of the chapter. want to wash all this off my hands, but there's no point. Look at my hands. I look like the Simpsons. I'm yellow. All right, that's what we'll start with this. I didn't look at the clock when I said that. I don't know when 15 minutes is up. What time was it when I said that? If I look at the, all right, well, try to judge when everybody comes back. Is there a periodic table in this electronic book? I'll see one in here. I just realized. I can't find it. The physical book has one on the inside front cover. But I don't see anywhere that you guys would find it. Yeah, I better upload that too.
Professor, do you have any of the periodic table charts left over?
I have a few more of these. Anybody else want another one?
This is periodic table.
Yeah. Did you guys, did I hand out the sign-in thing? Yeah. The sign-in chart still floating around? Did everybody sign? Everybody sign. Anybody else want to sign it? So for chapter 3, I want to start here. So you guys said you took chemistry before. You remember the word mole. Do you understand what a mole is? Okay.
Like pretending that I do.
Me too. No, it's actually, there's actually a few reasons why it's confusing. Down. Write that. Let me give it a shot here. Let's say I looked this up. Let's see. Okay, pretend this is true. It's somewhere close to true. 2,394 grams is how much 1 dozen apples weighs. 12 apples. Dozen means 12, right? All right. So let's say I pull up my huge flatbed truck at the apple orchard, and I say I want, what would be a good number? What's a huge number of apples that would sit on an apple truck? Let's say it's a dump truck, and we're just putting apples straight in there.
5,789.
Just to stick to your number. If I wanted it in dozens, what number would I use? That divided by 12 is 482. That still seems small. I want some number of dozens of apples. Let's do like I have no idea.
20,736 will work out nicely. 12, I think.
I don't want it to work out nicely. I want it to be kind of messy.
Oh.
Let's just say, let's just go with, I need that many apples. I pull up my truck, so what do they have to do? They have to go to their big pile of apples and start counting them, because that's how many dozen I want. They're going to have to count out 12 times that, but let's just say they're collecting them up 12 at a time. You can take them all day. You ever seen one of those industrial scales that you can pull a vehicle up on? If you go to the dump in Dahlonega, they weigh your vehicle on the way in, and then they weigh it on the way out, and it's X number of dollars for whatever you dump there. Like if you want to dump a couch or whatever. But if they have that, and I want that many apples, and this is known, I can drive up my truck, they can hit tear, and I can go, doing this right? That many apples. Yeah. So I would go, now, 1 dozen apples weighs then it's easy. They can just pull a hopper over and start dropping apples in there until, doing that right? Yeah, because I've got dozen apples, that will cancel. And I'll get 2, 3, 9, 4, 5, 9. That's a lot of grams. 4 significant figures, so I'm going to go for 2. So they're just going to drop apples into the truck until the scale says that. So the whole point is we've got apples by weight to apples by number. That's the difference between this and this. This is by weight and this is by number. Maybe if I did this as tennis balls, it'd make more sense because every tennis ball would be the same exact weight, so every dozen tennis balls would be the exact same weight. And what I'm getting at is The only weird thing about it is a mole is a huge number. But if I want a certain number of oxygen atoms, gotta erase this. Instead of grams per dozen, I need grams per mole. So this time it's not 12, it's 6.022 times 10 to the 23rd. And this is an integer. Don't get fooled by the dot this and that. It's not fractional. Once you multiply this by 10 to the 23, it's just a huge number, but it's an integer just like 12. So if that's a mole, I should have said this already. What did I tell you the grams per dozen were for apples?
2394.
Grams per 1 dozen of apples. And then, what was the number of dozen I said I wanted?
5,934.
All right, and this was 14 million something.
14,921,000. 0.
Okay. When I did this calculation, the number 12 didn't show up anywhere. I never needed the number 12 to do this. You see that? And in the same way, this number's not going to show up in what I'm about to do. What you need, like for my apples, I needed to know this general statistic about apples to do this. And then I could name how many I wanted, and I could get them. Or I could do this. I could go, I need, that one's 14, let's say 11. Let's say I wanted 11 million grams of apples. But before I got back to my market, wherever I was taking my apples, I was going to need to know how many there were in dozens. So then I would just use this upside down and go, and that'll tell me how many dozens I have. Let's say I'm taking them to a factory, put them in boxes, a dozen per box. Now I know how many boxes I need if I calculate that out. Does that make sense? But again, the number 12 doesn't show up anywhere. I never punch 1, 2 into my calculator anywhere. Okay. If you look at the periodic table, the ones I gave you, I guess they have them up there too. 16. So that 16 that you see for the oxygen, (16 grams per mole). So in some sense, the weird thing about the mole is you're not really supposed to picture what a mole is. The number's too huge. But the truth is it doesn't show up in most of the calculations we do anyway. The 6.022 times 10 to the 23rd, that's not going to show up in what I need to do with this. Grams per mole. So if you wanted to understand a mole, it's just a number. It's a counting number, like it's a counting number like dozen, like a pair. Score means 20. It's just like those, exactly like those, except it's just a huge number because atoms are so tiny. To get even a gram, it's still very, very tiny amount. But you would have, you know, a huge number of atoms just to get a gram of it. But that's what confuses people, is that doesn't always show up in calculations. In fact, the whole point of using mole is our as our counting number is to avoid having to do huge numbers like this. So once you have this from the periodic table, the grams per mole, also can be written that way, grams per mole for oxygen. That's generally all we need to do what we need to do, because then we can walk up to a scale and put a certain number of grams in there, and then we know how many atoms we have. But where the rubber hits the road, I'm starting in section 3.4 here. I felt like I had to say something about what the mole is. Really want to get to where we use grams per mole. I just looked at this. Okay. AMU is interchangeable with grams per mole, and I just want to get to the grams per mole rather than writing it as AMU. Finally. All right, calculate the number of moles. This is the type of question I want y'all to be able to answer. Calculate the number of moles. Okay. We have to do something before we can answer this. Calculate the number of moles of glucose, that's glucose, in that many grams. We have to do this first. What is it? C what? How many carbon atoms?
6.
H?
12. 06.
06. All right.
I think that's glucose.
So one molecule, I could draw that out, but I'd draw 6 carbons. There'll be some 6 oxygens somewhere and hydrogens all around. But you've got the molecular formula. You can find out how much that molecule weighs in grams per mole by adding it up. So on the periodic table, what do you see for carbon? Look at the one I gave. It says 12.01. And what does it say for hydrogen?
1.01.
Oxygen, they use 16.00. Okay. 6 times 12.01, what is that? I think it's, is that right? I just did that in my head. Sometimes I don't do that well. What is 6 times 16?
96.
6. Worth pointing out here, these are exact. So this multiplication here, you're paying attention to significant figures here. So I needed 4 here. Actually I have too many here. So that 12 is exact, and I've only got 3 significant figures here. So really I have to do that. And then that's 4 significant figures, so I've got that. And now I'm going to add them up. 1. Is that right? 96 plus 12 plus 72, that's definitely not right. 10. No, that's right.
That's what I got, yeah.
Okay. But I've only got one after the decimal there, I've got 2 there and 2 there, so I can only keep 1 because this is addition subtraction rule. So I'm only going to keep that one, the 6 rounds it up, so I have to do this. I could have put grams per mole there, and grams per mole there, and grams per mole there. But I usually leave it off and then just calculate it up. Grams per mole, grams per mole, grams per mole. I have to stick it on at the end. All right. That we need to answer this question. So this is how much, what was it, sucrose? Glucose. But again, I would tell you to do this. Grams, I'll say glue. So we need that to do this calculation. So you'll always have a periodic table, and if you've got the molecular formula, you can figure out the grams per mole of that molecule. And then the rest is like this. Calculate the number of moles of glucose, 5.380 grams. Keep my label. I need grams on the bottom, so that's going to be on the bottom. So if you crunch that out, that'll tell you how many moles. It's kind of like saying how many dozen, but it's how many moles. I guess they do this for us. So I suppose that's what we get. 4 significant figures. 4 significant figures, 4, yeah. The 1 mole is exact. So when you say 12.01 grams to 1 mole for carbon, the 1 mole is exact. And these are your significant figures. These are exact as well. Those types of numbers are exact as well. Okay. So questions like that, I think I want to skip those questions too. So really, that showed up right at the end of section 3.4. So I just uploaded a sheet that had all these questions on them to go over. But if you want exercises to practice this stuff, let me double check and see what's there. 39. All right. So it's 35, 36, 37, 38. This is cadmium sulfide here. All right, so what if I wanted to do this one? You would have to find, so we have to know the grams per mole. Cadmium sulfide. CD is cadmium. You know where S is. So where is cadmium? Can you find cadmium? Where's cadmium? There it is. Okay, so if I wanted to solve this one, so what does the periodic table say for cadmium?
112.41.
And there's only one of them in that formula. And then what do you see for sulfur? There's only one of those as well.
32.07.
32?
0.07.
All right. But this is just 112.41, so times 1, but let's just add them up. 7, 8, 4, 4, 4. Is that right? 144.48. I think that's right. So now that we have what we need, mass in grams of 1.50 times 10 to the negative 2 moles. And then moles on bottom. That's how you would solve that. That's how you get the number of moles. There'll be 3 significant figures. I'll finish it out. So equals 0.50. I'm going to put my power of 10 next, 10 to the negative 2. And of course my units are mole, gram, mole. All right. If I do that, my calculator gives me 216.72. 10 to the negative 2 grams. 3 significant figures, 5, so this needs to be 3. The 7 rounds the 6, so 217. What if it said, put it in scientific notation, or standard scientific notation? If the decimal is here, we need to move it twice. 10 to the negative 2 times 10 to the 2, and I still have that. If I do that, I get 2.17, and these just cancel each other out. 2.17 grams would be the answer there, if you put it in scientific notation. So those types of questions, and then those lead into the next section. Quantitative information from balanced equations. Previous section said something about balancing equations. I don't find it all that instructive to make you balance equations, but being able to use the balanced equation is what's important. That seems like a short chapter. I suppose short enough. So just a quick descriptor. Let me just go to the exercises. We've got Yeah, I guess that works as how many moles of HF. But I don't want to do that. I'll do this one. I'm going to do this one. So 3.62. So now you're looking at a chemical equation. And I want to rewrite it for KO2. Plus 2CO2 put those two in together and they react and they become K2CO3 and O2. And what are the coefficients? 2 and 3. All right, these numbers, these are exact. We call them coefficients, and think in terms of moles. Just pretend that says 4 moles and that says 2 moles. And also realize those numbers are there. If I made you balance this, you would be coming up with these numbers. But just realize what they're telling you is there's 4 This 4 is referring to 4 of these. You can picture 6.022 times 10 to the 23rd of these stacked behind that one. And then again and again and again, and that's why there's 4 moles. But you don't have to think that way. The 2 means there's, the 2 there means there's 2 of these formula units. 3 means there's 3 of these. So we could write our chemical equations this way. It's just more compact to write them like this. But this makes everything balanced. So there's the same number of oxygens over here as there are over here, and the same number of potassium over here as there are over here, and the same number of carbons over here as over here. That's what the balancing is about. All right, now let me say this. If you've got that in front of you as a balanced chemical equation, what this really is a summary form of this. There's these two things and they have a certain relationship to each other. That relationship is 4 moles of KO2 to 2 moles of CO2. That's the molar relationship of these two things. And then there's another one, there's this one to this. So this relationship is there too. 4, I should say moles. And then there's more. I did these two and I did these two. Now I'm going to do these two. Here's the relationship. 4 moles of KO2 to 3 moles of O2. All right. So there's 3 relationships, but there's more. I'm going to put my left finger now here and go, there's these two. So it's CO2 to K2CO3, 2 moles 2 moles and then there is another one, there's these, so 2 CO2, 2 moles of CO2 to 3 moles of O2, and I was here, but there's actually one more. Now I'm going to move my left hand again and do these two, 2 moles CO3, 3 there. What this really is 6 relationships written in a summary form. That's what this really is. You see what I did? And truthfully, when you have a question to answer, like a question on a test or homework, it's only one of these 6 that you're going to need in particular. You usually don't need more than one for a typical question. So, oh, questions down here. How many moles of O2 are produced when 4 moles of KO2 is reactive? What do they ask? They're asking O2, the relationship of O2 to KO2. Where is it? At this one. So it's this one we need. O2 to KO2. And what's given there? They give you 0.400 moles of KO2. I'm going to use this. I'm going to put this on the bottom because KO2 is up here. And that'll do it. That'll tell you how many moles of O2. How many moles of O2 are produced when 0.400 moles of KO2 react? That's how you do it. You see? Does it make sense? And they could ask anything. They could go, and they probably do there. If I get so-and-so moles of this, how many moles of this did I get? And so there's that relationship. Or they say, I got so-and-so moles of this, how many moles of this reacted? So it changes the language a little bit, but you're just always relating 2 of these.
The answer would still be in 3 sig figs because those are exact numbers, right?
Yep,
Okay.
these are exact, so these are your significant figures, those 3. Okay, one more step here. I'm hoping there's one right below here. No, okay, good. So number B in this question says, how many grams of KO2 are needed to form 7.50 grams of O2? So we need our grams per mole now of at least a couple of these. I've forgotten what it asked. Okay, we're still relating O2 and KO2. We got to do this. Oxygen, this is for O2. There's 2 of them times 16, 32.00 grams per mole. And then for KO2, we've got 2 oxygens, it's 16 apiece. And what does the periodic tell you for K?
39.10.
39.10?
Yes.
All right, so there's only 1 K, so I got a 1 there. There's still 2 oxygens, so I've got 2 there. So we're going to get 32, and this is 39.10. So we'll come up to 1011. So 71.10 grams per mole for this, and 32 grams per mole for this. So now we can answer this question. How many grams, all right, how many grams of KO2, so let me do this first. Grams. So I'm going to get some numerical value there. All right. So that's what goes on the right side of the equal sign. How many grams of KO2 are needed to form? So 7.50 grams of O2 put that over 1. The next thing I'm going to need is the grams per mole for O2. So 32.00 grams The next thing I'm going to need is that molar relationship between O2 and KO2. Remember I said think in terms of moles for these? So moles of O2, 3 moles of O2 is related to 4 moles of KO2. All right, so grams of O2, those have canceled. Moles of O2, moles of O2, those have canceled. Now we're in moles of KO2. Next I'm going to need this. Moles, 1 mole of KO2 weighs 71.10 grams KO2. And that's it. You see? So we needed our grams per moles, and we needed the relationship we got from the balanced equation, but that's how you would figure that out. Okay, let's hope to at least get there today in lecture. So that adds a little bit more calculations. I'll round out a little bit more from chapter 3. Did I say chapter 2? We were in chapter 3. I'll round out a little bit more from chapter 3 Thursday, but I'll leave time for questions and review on Thursday because we have so much time. I'll fill a little bit of time with a little more lecture, but be practicing these problems. I put problems, what did I call it? Practice for test 1. Make sure you're getting comfortable with these. Practice test 1. I gave you a copy of that periodic table if you want to print your own. But be going through those problems. Certainly calculations like from chapter 1 will be on the test as well. And I can give you a list of those from the back of the book. I just haven't. But be practicing those. I guess I'll print the lab out for y'all, but y'all be here at 2. Upstairs in the lab though, not in here. We're actually going to do real lab stuff. Any questions? Yeah, I guess I'll just wait till lab to have it. Hopefully the video's still going.
I'm going to turn in lab 1.